Gotta prep this stuff. Alright, one last thing before I get back out into the shop area. Wanted to look through here to show you several things that you're not going to see exactly right. It's backwards. I'm not going to write it full. This is your standard AC voltage wave, like 60 cycles, 60 hertz that you'd have coming out of your wall. There's 0. Over here, you're 0 volts. Then negative volts, 1B, and then positive volts. Now, on your 240 circuit, 0 to here would be 120. 0 to there would be 120. So you'd have 240 volts total on that whole swing. But we're not even talking voltage at this point. We're just talking about the waves, the cycles. Now, if it's single rectifying, like a single diode, you'll see this, where half the wave is just plain cut off. Well, what did that do? That took half of your voltage potential and tossed it out. So when you have single rectification, one of the things you run into, say on a Briggs & Stratton, is you'd be measuring the AC voltage and hoping you have about 30 volts. 28 minimum works, but you're looking for around 30 volts. Why is that? Well, because you cut half of the voltage wave off. Okay? Now, if you have bridge rectification, which is full, then what it does is it tends to take the negative side and send it out through the negative potential difference on the other side, and they end up coming across this way. In other words, your full wave is still being created, but they're taking it and switching things around so that the actual potential difference can be made on the other side. They catch the full wave, they just rotate it. Yeah, it's funky, but it works. That's why you hear them talking about diode bridges in an alternator. That's one of the ways they're able to do that. And they'll have a ripple test. So if you have a bad diode, some of these little guys will show up down here instead. And you'll actually have AC voltage because there's a certain part of the wave that just returned with a bad diode. So the diodes block and they send it out in different. So you've got the plus side and the minus side, and the potential difference doesn't care as long as there is that difference. Potential difference or volts. You can create it on the negative side or the positive side, but the idea is to reverse it and send out the waves, all of them, in one direction. So you have single rectification where you're splitting it, you're just plain blocking the one negative wave, or the other one where you're able to grab all of the waves and send them out. Whether it's positive or negative, the bridge takes care of it. Now the other one, pulse width modulation, that's something that actually operates. These guys, you end up talking duty cycle quite often. But down here, and then of course here, hertz. Down here, pulse width modulation. And that often can be called duty cycle as well. Similar idea to here. More waves, more duty cycle, etc., etc. And there are places where Komatsu itself does that, where they measure things in hertz as far as how much they're putting out in each AC style signal. They increase the hertz that they send out or reduce it. Well, when they do it the other way, pulse width modulation, there's 0 to plus, and that's it. It's basically off, on. And how long it's on, duty cycle of course, determines how much amperage goes there. The longer, the more, and if you have the same number of peaks all the way across, so say this thing's operating at 50 hertz, that never changes. Where here and here, this can change slightly because that's the design of it. But here, they keep it at one continuous. What they change is how wide, how long it's on, not how often it's on, which would be up here, analog. They change how long each pulse is on. So you have two shorts, less milliamps. Long, more milliamps. That's the new digital way of doing things. It's instead of changing the wave that's already there, they're turning it on and off. It's more of a pure DC power. It sounds like a funky wave, and sometimes you can actually hear a buzz in it just as if it was an AC deal. But that's something that I wanted to kind of throw in there because there's there's converting AC hertz to DC, there's always a loss. That's why even with a bridge rectification, you have a 250 amp welder, and maybe you can only weld 160 or 180 amps DC. Well, there's a lot of resistance in there. There's a lot of diodes that you have to play around. But that's the purpose of it, is to convert the negative side into a positive, because to have negative, you have to have a positive. That's what the diode bridge is for, so both sides work to your advantage. And I'd have to sit down and draw the thing out, but there's negative diodes and positive diodes. And depending on how they're aimed, they can actually assist each other. Yeah, I understood it at one point in time. Right now, why don't I understand it? Because I don't care. When I'm troubleshooting, I know that it works, and I have a rough idea how it does work. And I don't care if it's working properly. Explaining it to somebody or even to me doesn't matter. The problem is when it fails, I have an AC. When a diode fails, I have an AC segment coming out that I shouldn't. One of the waves is a full wave, and it's not converted. Then we have a problem, because it takes DC system and cooks it. Now, if it's anything, it's an inductive coil or battery, massive problem. Capacitors, massive problem. Switches, lights, they don't care. If the voltage is the same, they couldn't care less. They really don't. So that's why you'll see, yeah, my headlights are a little weird, but everything's working fine. Why? On your lawn and garden tractors like this one I have out here, it has an AC system with a single diode in it. So on one side of the diode, I want to read 30 volts. And that goes through the diode, cuts it down to 14 or 15. It's unregulated, so the RPM of the engine changes its output. Changes your hertz. And on the other side, well, yeah, more hertz, more feed, more positive feed through the diode. And on the lighting side, it's a direct connect. It's all AC because the lights don't care. Incandescent. Now, if you, you got it. LEDs, baby. If they're designed to operate on DC and you send through their little transformer and switching system an AC current, woohoo! I gotta imagine that's gotta be pretty. Here's a short one for you for today. 7 minutes, 50 seconds. Catch you later.